Hi class, we are now in the last section. We're on 6.5c, reactions in aqueous solution. So if we go back, in chapter 5, we introduced a very important class of compounds called acids. Recall that acids are covalent compounds that ionize to produce H+, which is known as a hydrogen ion, or also known as protons. Why is it a proton? Because it doesn't have an electron. So as you go through in chemistry, you will see this more referred to more and more as a proton than a hydrogen ion. But they mean the same thing, so they can be used interchangeably. So they ionize to produce protons and a stable anion when dissolved in water. We often use ionic equations to show how acids ionize in water. So for example, if we look at these equations here, we have, this shows the ionization of hydrochloric acid and aqueous nitric acid. And you can see when they ionize is a fancy word for they're splitting into ions. And here is a common name of some acids here. We have hydrofluoric acid, hydrochloric acid, hydrobromic acid. Down here is phosphoric acid and acetic acid. This is a slide from one of my other classes. So when we look at acid-base reactions, they are reactions that form water. There is two products that are formed when you're dealing with an acid and a base. They are water and a salt. Now, a salt does not mean sodium chloride. A salt usually remains dissolved in the solution. So it's the leftover ions, not necessarily sodium chloride. Could be potassium chloride, could be other stuff. It is what is left over of the cation and the anion from what is not made of the water. So we have the proton and the hydroxide, and those come together to produce water. And then whatever is not part of that is left floating or floating in solution. That is a salt. So it's a general term, not necessarily used as sodium chloride specifically. The net ionic equation, so this would be a molecular equation. The net ionic for acid-base reactions is water. So this is the net ionic for acid-base reactions. Here's a molecular, and the molecular for an acid-base reaction produces water and a salt. So here's from another slides from another course of mine. It gives you a list of bases. It gives you acids, because we're going to talk about bases next. And if you can see something, you notice the sodium, lithium, potassium, calcium, barium. These are all from group 1 and group 2. So these are some of the bases and the names for them. And I found this might be helpful for people that are having problems with naming still. So here's the anion, the name of the anion, and then the name of the acid. So I found this while I was putting together these slides. So hopefully this might help some people who might have still some problems with naming. And it's a lot, I know that. Okay, so, so bases are compounds that produce hydroxide, that's the OH minus that you see here, in aqueous solution. Many common bases are soluble metal hydroxides. So if you see the metals, here's lithium, sodium, potassium, barium, the metal with the hydroxide. In water, these compounds dissociate to give metal cations and hydroxide ions. And here you can see where this sodium hydroxide dissociates in water, producing sodium hydroxide in aqueous solution. So this would be in aqueous, where you can see it starts out as solid. It kind of looks like salt, and you put it in there and it will dissolve. So for example, pretty much sodium hydroxide dissociates in water to produce sodium hydroxide and sodium and hydroxide ions. And this is a slide from one of my other classes. I thought this was cool because it shows a picture. You can see calcium hydroxide is used in the food industry to produce beverages and in dentistry as a filler for root canals. And you can see here's other ones. Here's aluminum hydroxide. That's not on the list over there. So that's another reason why I wanted to point this out. You don't need to know what Arrhenius is. That hasn't come up yet. So don't worry about that. This is a slide from something else. My main point for this slide is to show you another base that hasn't been brought up yet, and also to show you a picture of this where you can see what it looks like. And calcium hydroxide hasn't been brought up yet either. Okay, so neutralization reactions. Acids and bases undergo neutralization reactions. That's what they're called. Acids and bases, neutralization reactions. When you hear neutralization reactions, acid and bases. In these reactions, the proton from the acid, the hydrogen ion, combines with the hydroxide from the base to form water, as shown in this net ionic equation. So you can see in blue here. And this is the general formula for it. You have an acid, you have a base, always produces a water and a salt for now. So for example, we can look at hydrochloric acid reacts with sodium hydroxide. We can write this as a molecular equation or as a complete ionic equation. So in both cases, we see it here as molecular, we see it here as total or complete ionic equation. Remember, we have spectator ions. That would be the salt in this case. And then we can look at a second example, which is nitric acid with lithium hydroxide. Again, the hydrogen ion from the acid reacts with the hydroxide from the base, and it forms water. The remaining ions end up together as a lithium nitrate, and that is the salt. So remember, when we refer to a salt in a neutralization reaction, we're not talking about sodium hydroxide, sodium chloride. We're talking about whatever ions are left over that did not help participate in creating and producing the water as a product. So this is the salt. In general, we can describe the reaction of an acid and base using an equation of acid plus base reacts to form water and a salt. Like precipitation reactions, acid-base neutralizations are double displacement reactions. The hydrogen ion plus the hydroxide combine to form water, while the other two ions combine to form the salt. The driving force of the reaction is the formation of water. So that the wanting to produce water is what forces allows this reactions to go forward. The salt forms from the other two ions. So what I just said here, I'm giving you a visual so you can kind of remember what's going on. It's a double displacement that produces water and a salt. It is driven by the formation of water. This reaction wants to occur to form water. All right, so let's look at one more example. We write a balanced equation to show the reaction of sulfuric acid with sodium hydroxide. Include phase symbols. We begin by writing an unbalanced equation to describe this reaction. We follow the general acid plus base forms water and a salt. The reactants are sulfuric acid and sodium hydroxide. One product is water, and the other product is the ionic compound produced by the spectator ions. A simple way to balance neutralization reactions is to balance the number of hydrogen ions and hydroxide ions that combine. Since sulfuric acid produces two hydroxide ions, there must be two hydrogen ions. There must be two hydroxide ions that combine. So there must be two hydroxide ions to neutralize them. The two water molecules will be produced, adding phase symbols to give us a balanced form. I'm going to break this down in an example if this seems a little overwhelming. Okay, so let's take a look at this. These are slides from another class of mine. Write a molecular and a net ionic equation for the reaction between aqueous nitric acid and aqueous calcium hydroxide. So it's not necessarily telling you that's an acid. You should know that that's an acid first in the first case because there's an H in front, and that usually indicates that's an acid, and it's an aqueous solution. As well as aqueous calcium hydroxide, there's a hydroxide and it's an aqueous. Okay, so let's take a look. How do we do this? So the first thing, recognize that this is an acid and a base reaction. Acid and base equals neutralization reaction. This means that an acid and base, remember, neutralize each other out, and that produces a water and a salt. So you should remember the general equation for this. That part, once you remember that it's a neutralization, acid and base always forms water and a salt, that should help you be able to pull apart and determine what the products are. So here it is. I've given you number 2, set up the reactants and products. It may not be balanced. We're just putting it out there. Get into just putting a skeleton equation and doing this step by step. Do not let it overwhelm you. Okay, so now that we set it up, third part, add the physical states in. Why am I telling you to do this before balancing it? Because it would be really easy to spend a lot of time balancing this and then moving on. So before you balance, add the physical states in, because that is an easy way to mess up. When we're back in person, you'll have to do this stuff, because in next section of chemistry, you will be back in person in lab, at least. You will have to know how to do this stuff, and it'll be wrong. And it would really be a bad thing when you know how to do this, but you forget to put that stuff. Okay, so The reactants are both aqueous. It tells you they're aqueous in here. Now, because it produces water, water's a liquid. So you don't even need to worry. If it's an acid base, it produces liquid water. Then that means that the other ions are in aqueous solution. So you don't even need to look these up in this case for this example. I'm not saying in general, just in this sample. We're pretending everything just goes very easy where you don't have to do that. Okay, so you add the physical states in before you balance, because trust me, that's an easy step to mess up. Okay, so now balance the equation. So we balance it out. Here's the molecular equation, but we're not done because it's asking for the net ionic. So what would the net ionic be in this case? It's what produces water. So we pull that air, and if we notice, we got 2 and 2 and 2, so we can reduce this down, and that is our net ionic equation is down here. So this would not be done. This would be wrong. Yes, it's right, but it's not complete. So this would be dinged if we were in person. This is how it needs to be. It has to be completely reduced down. Okay, aqueous hydrobromic acid and aqueous sodium hydroxide react to form water and aqueous sodium bromide. Write a molecular ionic and net ionic equation for this reaction. Okay, so I'm giving you everything. Follow the steps that I previously gave you, and so that should help you. So break it down in steps. If you notice, what I did on this one is I numbered it. I kind of do that when I'm first learning how to do something, because if I can keep a checklist of learning how to do it, then it helps me not to miss certain steps like physical states, which have to be put in there. So that's where you see I numbered it. Okay, recognize, set up, add physical states, balance, and then finish whatever else it's asking for. So in these equations, these extra ones, you can do the same. Just follow the steps, pull out the information, follow the one, if it makes it easier, follow the steps like I numbered it, and then you can get to the end of everything it's being asked for here. Okay, show the products from the following neutralization reactions, balance if necessary. So these are ones I'm giving you to help you work on. As you can see, here's another one we haven't covered, is cesium hydroxide. And you just follow the same steps. Look it up, see where it is on the periodic table. It should be a metal. And that will allow you to go on and figure out what it is. So this one's a little interesting because you can see it looks a little bit more complicated, but it's not. It's an acid and a base. Do not let something that doesn't look familiar to you overwhelm you. Just follow the rules that you know them, and you can't go wrong. The net ionic equation for any aqueous and acid-base neutralization is, and hopefully by now I have gone over it so that you can catch it, it's A. What is the driving force for an acid-base neutralization reaction? That is the formation of water. It wants to form water. That is going to overrule everything else in some cases. So what we're looking at right now, it's in the case that's what it wants to be. We're not looking at exceptions. Okay, now I'm going to do a little bit of review from the other parts of this. I snuck this in, and hopefully it helps because there's a lot of sections to this chapter. In the boxes, describe the key features and give one example of each type of reaction. So here is just a review. You can see here's a metal and a non-metal. Here's a combustion, a precipitation, which produces a solid, and then a neutralization. These are double displacement reactions. So make sure you understand that there's a couple types of different double replacement reactions, and they produce different outcomes. What type of reaction is this? So I'm going to take a look. This has a solid in it. So I would tell you it's going to be a precipitation because that's not an acid and that's not a base, but it is a double displacement reaction. What type of reaction is this? Well, it's got an acid, it's got a base, and it's producing water. So it's a neutralization.